All right, Tuesday, Thursday people, this is our follow-up lecture from Tuesday where we were working on finishing up the urinary system. We actually are now dealing with the filtrate, its formation, and how we reabsorb the solutes and therefore also the water from the filtrate and put it back into our intravascular tree or network. Also, how we get rid of certain unwanted materials via secretion. So let's take a look here. Don't forget at the beginning of this section of maintaining concentrated urine, blood infiltrate in the upper part of the tubule is at 300 milliosmoles in both the blood as well as the filtrate, so both in the glomerulus and the first part of our filtrate. And it's important for us to realize that the osmolarity of the cortex is also around 300 milliosmoles. And when we are in the deepest part of the cortex, around the papilla of that pyramid, we're at 1200 milliosmoles. So the higher the number, the more salty you are, or the higher tonicity, so hypertonic. This is important because water movement is going to be very dependent upon this tonicity as we go through this. Remember, the descending limb of the nephron loop is impermeable to salts, but freely permeable water. Our ascending limb is impermeable to water and is going to actively pump sodium chloride out. The vasa recta is around the nephron loop and will be picking up whatever water and salt that is pumped out into that area that could be causing any sort of dilution, and also putting it back into our bloodstream, which is where we need it. So this is all about the countercurrent mechanism of the nephron as well as the collecting duct. So here we are at the very beginning. We're at 300 milliosmoles as far as the osmolarity of our blood. Now we have our filtrate. Remember, our afferent arteriole is larger in diameter. Our efferent arteriole is smaller in diameter. And the filtrate is a result of net filtration pressure of glomerular hydrostatic pressure pushing fluid out into that area because of the large afferent arteriole, increasing that glomerular hydrostatic pressure up to 60 millimeters of mercury. Osmotic pressure is going to be the pulling pressure back, and that is what we're going to leave that at around 30. And then our back pressure of the capsular hydrostatic pressure is 20. And so if we were to dilate the afferent arteriole, that would increase our glomerular hydrostatic pressure. And also if we were to vasoconstrict the efferent arteriole, that would also increase glomerular hydrostatic pressure because it will directly impact the flow of blood into the glomerulus, the volume. And the larger the volume of flow of blood in the glomerulus, the more we're able to squeeze on out. And then the less flow of blood into the glomerulus, the less we're able to squeeze on out, so we'll have a less filtrate actually formed. Now we're in the PCT, proximal convoluted tubule, and the osmolarity throughout the PCT is 300 milliosmoles. Remember, we have all of those protein pores that have that transport maximum, and so we're taking out glucose and sodium and vitamins and things along amino acids, and as those leave the lumen of our tube, so will water, because these are solutes and water always follows solutes, and the osmolarity in this area is around 300 milliosmoles. And so what's interesting is that we have the same amount of water leaving with the solutes that in relationship to the amount of solutes and water that's remaining. Now, as we go into the medullary area of our pyramids, we are going to now go into the descending limb of the loop of Henle, or the nephron loop, and we are going to not even actively pump water out, because as we go in, we are noting that the surrounding tissue is at 400 milliosmoles. Well, that's more hypertonic than the 300 that we had in the beginning, so we will pump water out. The more water, or not pump, water will leave, excuse me, and as water leaves, solutes will concentrate. And so as we go down into more hypertonic or hyperosmotic areas, more water is leaving, leaving us less water inside the lumen, but more solutes. And as we go further on down, we end up with 900 milliosmoles. And then when we get to the apex or the tip of the pyramid, we find that the osmolarity at the tip of the nephron loop is at 1200 milliosmoles. And so that means we lost a lot of water. And so now we have a lot of solutes, and this is a really salty filtrate now. And as we go up our ascending limb of the nephron loop, we are now no longer permeable to water. We are actively pumping out sodium chloride. Well, that's a solute. And so as we remove solutes from this high solute concentration, that dilutes it, and so our numbers go down. And that's what we see. And actually, even before we get into the cortical area, we are actually down to an osmolarity of 200 milliosmoles. And then once we get into the distal convoluted tubule, we're at 100 milliosmoles. And then we stop pumping sodium chloride out, and the fluid just moves on out through the distal convoluted tubule. And if there is no aldosterone present, or there is no antidiuretic hormone present, that volume of that filtrate will not really change. But if aldosterone is present, it has a fairly significant effect on the distal convoluted tubule and will cause us to actually reabsorb sodium. And when we reabsorb sodium, we'll also reabsorb some water. But if we stay at 100 milliosmoles, there is no aldosterone working on this area. Now let's go into our CD, our collecting duct. We're at 100 milliosmoles. The surrounding tissue of the cortex is 300 milliosmoles, but we're not permeable based upon this diagram here to water. And so 400 milliosmoles, we're still staying at 100. 600 milliosmoles, we're still staying at 100. 900 milliosmoles, obviously we're going to the apex or the tip of the pyramid, and we're still at 100 even in the 1200 milliosmole area. And so what's important is that antidiuretic hormone is going to be responsible for causing the insertion of aquaporins into the luminal side of the cells of our predominantly collecting duct, but also it will have some impact on aquaporins in the distal convoluted tubule. The difference, though, is because the cortex osmolarity is 300, that's the best that we'll be able to get with our filtrate. But because of the concentration at the tip of the papilla, or at the tip of the pyramid or the papilla of 1200 milliosmoles, if we put in all these aquaporins, we are going to definitely be pulling off a whole bunch of water. And the more aquaporins we put in, the more water we'll be able to pull off, and we can get an extremely concentrated urine. And so this is if we actually were exceedingly dehydrated and therefore releasing a lot of antidiuretic hormone. We have all these aquaporins in, we'd actually have a maximally concentrated urine. Now, in kangaroo rats, they have a more concentrated papilla or pyramid. They're actually at 2400 milliosmoles at the apex of their pyramids, and so they can double up actually on the osmolarity of the final product, which is urine that's actually being produced. And by doing that, they actually have very little urine produced because the volume of water that is lost is actually low because it's actually all reabsorbed because of the antidiuretic hormone effects. And so that's why for us to change the concentration of our urine to go from a dilute urine to a more concentrated urine, we need antidiuretic hormone because it will cause aquaporins into the luminal side of our, let's go ahead, of our DCT, but more importantly, collecting duct, because that's the one that's got the saltier surrounding environment in there. And when we have any loss of water from our system or our body, this results in ADH release, and therefore retain more water because we reabsorb it, because we have more aquaporins that are being inserted into our collecting duct. The fluctuation of our ADH levels will cause, therefore, the fluctuation of the actual formation and concentration of our filtrate as well as, therefore, our urine. So forming a dilute urine, we can decrease ADH secretion. That's the most common way we actually form a dilute urine. And so then that will give us a decrease in aquaporins of, and I'm going to put CD first, collecting duct, because that's the one that's most important, and then DCT. This will make these structures less permeable to water, leaving the luminal side of the cells, and so this water is actually then retained in the filtrate and then flows out at the papilla in the form of urine. So this will increase volume of final product, which is urine, and decrease osmolarity of urine. And that's what forming a dilute urine is all about. Now, diuresis is also another way we can form dilute urine. Diuresis means to pee more, and to pee more means a larger volume of water. And we have two culprits that are in our environment that we can actually ingest that will actually cause a diuresis for us. One is alcohol, and alcohol inhibits antidiuretic hormone release. And so even though alcohol is a desiccating or drying agent itself, when you inhibit antidiuretic hormone release, then that means less aquaporins and therefore more water actually present in the filtrate and a final filtrate and therefore urine. Caffeine. Caffeine inhibits sodium reabsorption. And it's important to realize that sodium is reabsorbed the entire length except for the descending limb of the loop of Henle or nephron loop throughout most of our collecting duct there, collecting system, excuse me. And when we reabsorb sodium, we typically reabsorb water. So if you inhibit the reabsorption of sodium, you will inhibit the reabsorption of water. And that's how caffeine causes us to actually diurese or pee out more urine. Chemical composition of urine, no surprise, 95% water and 5% of it is actually solutes. And of the solute load, mostly is in the form of urea, which actually comes from the breakdown of proteins. And so our kidneys are very important in helping us to get rid of this byproduct of protein catabolism. We're finishing up on the structures of the urinary system, the ureters, urinary bladder, urethra. We all know now what's in these structures. That is actually the final product, or urine. The ureters themselves have a mucosa. And of course, the epithelium of that mucosa is, not surprisingly, transitional. And then we also have a muscularis, which is very important because the ureters are going to have peristalsis to help move the urine from the renal pelvis down the ureters to the bladder for storage until it's time to void. And we also have the outer layer is adventitia. And this is because all of the urinary system is retroperitoneal. So we have no serosal surface. We have an adventitial surface, and whenever you see adventitia, you should think that it's not in some sort of serosal lined area or cavity, and most often is retroperitoneal, except for our esophagus and our trachea. They are also covered with adventitia, and they're not in a true cavity. They're actually in that mediastinal space, so that's why we have that. Okay, don't forget peristalsis. Conducts urine to bladder. It doesn't matter if you're standing up, laying down, or on your head. Urine is actually going to be pushed towards the bladder. Now, the urinary bladder indeed is a muscular sac. It is located on the pelvic floor, often referred to as pelvic diaphragm, and so this is the female's pelvic diaphragm, and this is the male pelvic diaphragm in this picture. So it's easy to recognize the female. The urethra itself is rather short, just a few centimeters, and in the male, we actually have 3-fold to 4-fold the length of the urethra, and various structures are also encountered along the length of the urethra for the male. We have a area at the base of the bladder. That's called the trigone, and so we'll find openings for the 2 ureters and 1 urethra, hence trigone, or 3 things. And so here we are for the ureteral openings. Here is the urethral openings. Urethral openings. I do recommend, if you haven't already done this, open up your cat's bladder and see if you can identify the cat's trigone area. It'll be obviously much smaller than we have with the human, but still identifiable, especially if you follow the ureters and see where they insert into the bladder, and then also the urethra. You should be able to actually see that. This is an important thing to realize. This placement is very necessary to prevent reflux. So instead of the ureters actually going to the top of the bladder, they go to the base of the bladder. As that bladder fills and becomes heavier, it actually closes or pushes close those urethral openings, and that helps to prevent reflux. And so indeed, we need peristalsis to go ahead and squeeze or milk urine as it is being formed into the bladder for storage. Now let's go ahead and just erase a few things here and look a little bit more at our notes. But before we do that, let's take a look at the female and male bladders and find out if there are any sphincters present for these structures, and how many and where are they located. As you look closely, you will find an internal urethral sphincter present at the base of the bladder, associated with the beginning of the urethra in both the male and the female. And there is an external, so there are 2 sphincters. There is an external urethral sphincter present, but it happens to be in the pelvic floor or urogenital diaphragm area. And what's important to realize that there is less space between the internal and external urethral sphincters in the female than there is between the internal and external urethral sphincters in the male, because in between the internal and external urethral sphincters is the prostate gland. So the prostate gland is underneath the base of the bladder. Then we have the pelvic floor or urogenital diaphragm, and then we have the rest of the urethra, which is located within the spongy area of the male penis. So it is a little bit longer or further away, but it is still in the very same tissue that we actually saw with the female. Again, erase all that for you. Let's go down to the notes and see what we have to review before we finish this material. Bladder wall, indeed, transitional epithelium folded into rugae when it is empty. When it is full and distended, just like the stomach, the rugae actually seem to disappear. We have a muscularis layer, which is indeed smooth muscle, and the muscle of the bladder is very special. It has its own name. It's called the detrusor muscle. So that is indeed the smooth muscle of the bladder. Adventitia is the outermost layer of our bladder. And indeed, this makes sense because it is also retroperitoneal. Moving now externally towards the urethra, our notes state it's a thin-walled tube that drains urine from the bladder. Its wall has a fibromuscular aspect to it. We still have smooth muscle in it because there is still some peristalsis that actually occurs within the urethra itself. The mucosa, mostly pseudostratified columnar in male. That is not so for the female. When we are close to the bladder, it's transitional. And then when we are close to the external opening, it is stratified squamous. And when we take a closer look at the sphincters of either the male or female, internal is composed of smooth muscle, involuntary control. External is composed of skeletal muscle, and that is going to be under voluntary control. And let's go ahead and talk for a moment about micturition and the micturition reflex, which is also referred to with micturition as voiding or urination. What happens is when 200 cc's or mLs accumulate in the bladder, it activates stretch receptors of the detrusor muscle and causes that muscle to contract at the same time, causing relaxation of the internal sphincter. So your internal sphincter will relax, and unless you voluntarily relax your external sphincter, you will not void. And so that's a happy day with your little kids when they learn that that external sphincter is under their voluntary control. Then parents don't have to spend so much money on Huggies or pull-ups or any of those types of child wear. Now, the stretch relaxation response is very prevalent in the detrusor muscle or the bladder, and so you can actually basically give negative feedback about the reflex here and tell it, no, we're not going to do it when we do not relax our external sphincter. And so what will typically happen is we'll double the volume of urine in the bladder, and again, we'll get the micturition reflex actually almost forcing us to go ahead and void, or to definitely let us know that it won't be much longer before we're going to have to. So the bladder is a very happy organ to accommodate you, and you can actually teach it to actually hold more fluid over time. So now let's go ahead and, oh, by the way, that is the end of the content that will be covered on exam 4. So now let's go ahead and take a look at what is chapter 25 in McGraw-Hill and talk about fluid and electrolytes, which is perfect after discussing the kidneys. So body fluids, total body water is related to age, also to sex, and to weight, as well as, shall we say, obesity or fat content. So who has more body water? A little kid or a geriatric individual? And most everybody automatically will state that it's the little kid. So they have more total body water in comparison to solid material. So related to age, composition-wise, percentage-wise, younger have more and older have less. Sex, what's really interesting, it's the sex aspect is also has a direct relationship to the weight of the individual and the amount of total body fat. Because muscle tissue has more water associated with it than fatty tissue does. And so the more muscular the individual is, the more water they will actually have in them, and the more fat an individual has compared to muscle, the less percentage-wise of total body water they will actually have. So even though we think of women having more water, total body water associated with them, the more muscular the individual, which is typically male, actually has more total body water percentage-wise than women do. Let's go to our fluid compartments and analyze them. Intracellular compartment is going to be abbreviated ICF, so intracellular compartment of fluid, and extracellular compartment is extracellular compartment of fluid. And amazingly, we actually have the most of our fluid in the intracellular fluid space. So approximately 2/3 of all of our total body water is inside our cells. Total body water, TBW, excuse me. Extracellular compartment, therefore, only has about 1/3 of our total body water, and it is going to be divided into the interstitial space and the plasma. And approximately 2/3 of the extracellular fluid is actually in the interstitial space. So the plasma, which is 4 to 5 liters of blood, depending upon our sex, is indeed the smallest component here of our fluid compartmentalization. Composition of body fluids. Let's take a look. Well, we know that there's lots of solutes in our body fluids, and solutes, no matter what type they are going to contribute to osmolarity. We are going to divide our solutes, or our particles, into those with a charge, which are electrolytes, and those without a charge, which are non-electrolytes. And so if you have a charge, that means that there were 2 parts to you. You had a positive and a negative charge, and this molecule dissociates or separates into the individual charged particles in solution. So often we will refer to our electrolytes as ions. The non-electrolytes, or those solutes without a charge, those are going to be our organics. So our organic molecules that do not dissociate. And this will be glucose, for example. We'll have urea. We'll have lipids and creatinine. Those are the non-electrolytes we want to realize. And so all of those guys are solutes. Now let's take a look at some of the intracellular and extracellular fluids, and more specifically the ions that play a predominant role in our solutes of our fluids. So extracellularly, the main ion that is the cation, is sodium. So cations have a positive charge, and the main anion is chloride. So anions have a negative charge. That's the main ions that we find in our extracellular fluids. And the ionic movements are very important in our osmotic story or history. Intracellularly, our main ions, as far as the cation goes, that's potassium. And then inside our cells, or intracellularly, our main anion is our phosphate anion. So a -2 charge on that. Now, fluids will move between the intracellular and extracellular compartments based upon various osmotic and hydrostatic pressures. And so that's what we've been talking about when we talked about capillary dynamics, and also when we talked about net filtration pressure with the kidneys. So osmotic, remember, is that pulling pressure based upon particles, pulling water to it, and hydrostatic pressure is more of the pressure that's related to the weight of water, or the pushing aspect of blood pressure and things like that related to water. So let's see here. Realize that anything that will change various ion concentrations will cause a change in our water movements or water concentration. Ion concentration. Cause water movement. And things that can change ion concentrations are basic diffusion processes or even pumps like the sodium-potassium pumps. So now we're into water balance. Water intake must equal water output. And let's take a look here. It says that we take in approximately 2.5 liters a day of fluid, and we put out approximately 2.5 liters a day of fluid. And the larger the person, obviously, the more this resembles this story, and then the smaller person, obviously, less intake and less output. So we'll deal with this 2.5 liters a day. Okay, most of our intake for fluid will be in the form of liquid or drink, and down here we have about 60%. And then we have fluid in our foods. Our foods taste terrible when they are dehydrated and not rehydrated. So 30% of our fluid intake is via the food. And then we also have what is called metabolic water. And metabolic water is that which we get from chemical reactions. And the chemical reactions that we're actually referring to are our dehydration synthesis reactions. And so when we make things, when we put things together, we'll actually then have a byproduct of water as far as chemical reactions go. So what regulates our intake? Well, anything that increases our blood osmolarity, and which is which will reflect osmolarity of other tissue areas, because one of the things that's important about our extracellular fluid compartment and our intracellular fluid compartment, they are basically in contact with each other. And so when one area is impacted, other areas will also feel it as it's trying to reestablish fluid dynamics and composition or concentrations of various ions and solutes, either inside or outside of the cells. So anything that will increase our osmolarity will stimulate the hypothalamic thirst center. And that's one of the functions of the hypothalamus. So we indeed have a thirst center in the hypothalamus, and it works very well for most of us. The sadness is it seems to get a little spotty in its functioning as we get very aged. And so that's one of the problems for a lot of geriatric people. They don't feel as thirsty as they should, even though their osmolarity is increasing and they don't drink enough water often. Output. Okay, going back up to our picture up here, it says that we breathe out fluid whenever we exhale. We also lose some fluid in our sweat. We lose fluid via our skin, and remember that's one of the main reasons why we actually have skin and why we have keratinized skin, to actually keep us from desiccating or dehydrating out. We lose some of our fluid in feces. Whether if you have diarrhea, obviously you're going to lose more fluid. If you have constipation, you'll lose less. And then we will lose our fluid in the form of urine. And there are two categories here about urine. One is obligatory and the other is facultative. So let's take a look at what that means. Before we do that, percentage-wise, lung and skin, about 28%. Sweat's a small amount. Fecal material is twice as sweat, and urine output happens to be very similar to our fluid intake of 60%. Our regulation of our output is definitely going to be greatly impacted by our kidneys and is going to be tied to sodium movements also. And our urine output is greatly affected by presence or absence of very important hormones, mostly antidiuretic hormone or ADH, as well as aldosterone. We have a couple of things to look at real quick here. With water loss from the kidneys, we have what's called an obligatory water loss and a facultative water loss. And the obligatory water loss means that it cannot be regulated. We are obliged to lose this no matter what our water intake is. This is definitely related to our kidneys. Kidneys must make some urine every day. And so that is one reason why if somebody's on their deathbed, they aren't eating, they aren't drinking, but yet their kidneys are still causing formation of urine. It gets super, super duper concentrated, and that's because the kidneys are obliged to actually function and make that urine. Once that urine formation actually declines dramatically, then that means that kidneys are no longer functioning well for them and are failing, which is to be expected when we pass. Now, the facultative water loss is going to be dependent upon our water intake. And so if you're drinking a whole bunch of water, if you're drinking 8 glasses a day, you're going to have a lot more urine formation than if you're drinking just a couple of glasses a day or a cup of coffee or 2 a day. So let's go ahead and now take a look at electrolyte balance. We could also call that salt balance because whenever we talk about sodium chloride, that's an electrolyte and that's a salt, and that is indeed our main solute outside of our cells. And sodium chloride most often must be pumped and is the main controlling solute in our extracellular fluid. And here we see our blood, this is basically our blood sodium level, ranging from 135 to 145. I have a tendency to just remember 140. because that goes with pH of 7.4, so 4 sticks in my mind quite a bit. Our sodium balance has a dietary aspect to it as far as our intake, and then our output will also be determined by the functioning of our kidneys, also what's in our fecal material, and whether or not we're sweating a lot. Here is the list of hormones that actually regulate sodium concentration within our system. Aldosterone, that causes us to reabsorb sodium and water. That's what means retain sodium and water, and will be responsible for helping us to maintain sodium blood plasma concentrations and osmolarity. Antidiuretic hormone, that causes us to retain water, and the more water we retain, we'll dilute ourselves out and will decrease our sodium blood plasma concentration. We are going to talk a little bit more very soon about ANP, atrial natriuretic peptide. That actually increases the excretion of sodium and water. It reverses all of the mechanisms for sodium and water retention. And by doing so, will decrease sodium blood plasma concentration as well as fluids. Here is a nice cartoon, the sodium concentration and regulating fluid balance. If we have low water or increased sodium concentration, that means that we are hypertonic or hyperosmolar, and that means water wants to move into the bloodstream from our intracellular fluid compartment. So if we're dry intravascularly, our intracellular fluid compartment, which is so full of water, will try and help dilute us out before we even drink any water by shifting some of their water into the bloodstream. The opposite will actually occur if we become hypotonic in the plasma. That means we have too much water in our bloodstream or too low of a sodium concentration, and so because we're too wet, the fluid will try to actually balance out and go inside the cells, trying to bring our osmolarity and tonicity back to where it should be. So this is an important cartoon that shows us how fluid movements play a role here between the intracellular fluid compartment and our blood plasma, which is our main method to keep an eye on our extracellular fluid compartment. So let's take a look at aldosterone. Causes sodium reabsorption in the kidneys, and therefore water follows. Remember, it is released from the adrenal cortex, and is a mineralocorticoid. Aldosterone is part of a very important mechanism called the renin-angiotensin-aldosterone mechanism that will bring about aldosterone release. There's two main methods for aldosterone release, and the renin-angiotensin-aldosterone mechanism is one of those. The other mechanism for the release of aldosterone is high potassium levels. So high blood potassium levels will stimulate aldosterone release. So two mechanisms, renin-angiotensin-aldosterone mechanism and high blood potassium levels. One of the things that happens when aldosterone is released, we save sodium and save water, put it back into our intravascular tree, and we excrete potassium. So aldosterone does that for us. One of the things that will stimulate the renin-angiotensin and therefore aldosterone mechanism is a drop in blood pressure. Will cause renin release plus a drop in osmolarity. Once we release renin, that will stimulate the formation of angiotensin. And then angiotensin will stimulate the release of aldosterone from the adrenal cortex. So that's how aldosterone release comes about. And remember, potassium is excreted for our sodium that is reabsorbed. Okay, antidiuretic hormone, we know that causes the reabsorption of water by the insertion of new aquaporins into the channels, the luminal side of our distal convoluted tubule, and more importantly, our collecting duct. Osmoreceptors in our hypothalamus are responsible for sensing solute concentration changes and will cause either the release or inhibit the release of ADH. So osmoreceptors increase or decrease ADH release from our posterior to pituitary. Then ANP, atrial natriuretic peptide. It used to be called atrial natriuretic factor in some older texts, and also atrial natriuretic hormone. So you may see it in that form. We will try to remember to always do it as ANP because that makes sense for us. What's interesting about ANP is that it inhibits almost all events that increase sodium and water retention. And so it will suppress the release of renin. It will suppress the release, therefore, of angiotensin, aldosterone, and antidiuretic hormone. So suppresses their release or therefore their formation of any of those four hormones. So whenever we are not able to therefore retain sodium and water, then we will lose it, and this will cause a diuresis for us. Again, potassium is our main solute inside of our cells, and its level is really controlled by the kidneys. If we have an excess of potassium in our extracellular fluid, this will cause aldosterone release. With aldosterone release, again, we're saving sodium and therefore water and excreting potassium, thereby bringing ourselves down to a more normal level of potassium, which is typically a 4.0. The problem is if we have excess potassium in our extracellular fluid, this affects our ability to repolarize. Because remember, low potassium levels in the extracellular fluid will allow us, when we're repolarizing our cells, those potassium gates will open and potassium leaves, helping us to reestablish a resting membrane potential voltage quite quickly. What's interesting, though, is if we don't have enough potassium, because excess is bad for us, and also a deficiency in potassium is bad for us. So if not enough potassium in our extracellular fluid, what will happen is potassium moves out of the cell, causing the cell to hyperpolarize. The reason potassium is moving out of the cell is because if it's low outside the cell, we can go ahead and give that potassium to the cell, potassium from the cell. We can let them have a little bit of our intracellular potassium to help normalize or stabilize potassium levels outside of the cell in the extracellular fluid and therefore in the blood plasma. This is a problem because we're hyperpolarizing our cells, making it harder to cause our neurons to fire or even our heart muscle cells to fire. And one of the things that will happen is, in order to rebalance the cell, protons or hydrogen ions move inside the cell, causing acidification of our cells. So we're trying to electrically balance the cell back to the resting membrane potential by doing this. Again, aldosterone directly potassium directly stimulates aldosterone release. And so this secretes it into the filtrate, which will be excreted in our urine. And this is actually done. This is easily done whenever we have a normal pH. But if we are acidotic, except during acidosis, what will happen is aldosterone and acidosis will cause proton or hydrogen ion secretion or excretion instead. So an acidotic pH is, we try to actually stabilize or normalize that metabolic acidosis by actually using protons as a substitution for potassium when aldosterone is present, which will be increased during severe stress for us. So that leads us to the end of this chapter, acid-base balance. Alkalosis. Blood pH above 7.45. Acidosis, blood pH below 7.35. Normal pH for us is 7.4. We have several different buffering systems And the one that's listed first is the one that we rely on the most, and then the others that are listed will help out, but don't help us out as much as the first one on the list. So chemical buffering systems are the one system that we have that is designed to help minimize pH changes for us. Our chemical buffering system is going to buffer a strong acid by converting it into a weak acid, which means less protons, or a strong base, and we'll buffer it by trying to convert it into a weak base, therefore resisting pH changes for us. So let's take a look at our little items here in the chemical buffering system. And we have carbonic acid on one side and bicarbonate ion on the other side. So we have much more value from the bicarbonate buffering system than we do from the carbonic acid system, but it is this equilibrium. What this means is, as far as equilibrium goes, we have this as a weak acid, which means it doesn't move this direction very readily, and produce protons as well as the next buffer, which is the bicarbonate ion. So let's take a look at this. H2CO3 is carbonic acid. It is a weak acid, which means it doesn't separate or dissociate into protons and bicarbonate. And then our weak base, if we took sodium off of this, we would see this, but it's more commonly seen in our system as sodium bicarbonate. So hear that word bicarbonate and realize that we have a weak base that is going to be helpful in getting us being used to help minimize pH changes. So let's take a look first at sodium bicarbonate. So NaHCO3 will dissociate into HCO3, which is our buffer, and that buffer can accept protons. So this is a weak base is what we're making here, which is going to help us with buffering an acidotic situation. So let's add a really strong acid. Hydrochloric acid plus, now we're going to pull this guy in, HCO3 will, and realize we, actually let me erase this. Let's go ahead and put our sodium, HCO3, sodium bicarbonate. When we combine this very strong acid with this very weak base, we will get a very weak acid, H2CO3, plus salt. So we've effectively buffered this really strong acid by making it a weak acid by the addition of this very weak base. Now, let's take a look at a very strong base, NaOH, sodium hydroxide, plus a weak acid, H2CO3, carbonic acid. And what we will do with this process is we will get sodium, NaHCO3 bicarbonate, which is a weak base, plus H2O, water. So we've taken a very strong base and we've essentially made it a very weak base, which means we've minimized those pH fluctuations by doing this. So this acid is a buffer, and this weak base here is the buffers that are prevalent inside our bloodstream. And remember, we have this chemical reaction up above being promoted in our red blood cells by carbonic anhydrase. So that's one of our buffering systems. That's the major buffering system that takes care of things right away. Minimizes any sort of pH changes by whether or not we're having a bunch of protons or hydroxyls in solution. Now we have another buffering system called the phosphate buffering system. Works very similar as the bicarbonate. However, there's a problem here. We have low concentration in the plasma, so not much effect here. So it's not a very important buffering system for us, in other words, but for the bloodstream and blood pH. But we have a high concentration in the urine and the cells of the urinary tract, and it means it's a good buffer here. And that's important because remember, we can secrete protons into the filtrate, and when we do so, we need to actually have that buffered. So the phosphate buffering system is really nice. Protein buffering system. This is still part of the chemical buffering system that we have. And what's important is proteins are made up of amino acids. So amino acids. So one end of the amino acid molecule is the acidic end, which means it will donate protons, which we see right over here. And the amine end is our basic, so here's the acidic, here's the basic or alkaline end, and what that means is that it can accept protons, and so that's what the protein buffering system is all about, because we have proteins in our blood. Remember, albumin is one of those proteins. So we have RCOOH, that's the acid side, can become RCOO plus H plus. And so what's nice about this acid side, if we are too alkaline or the pH is too high, that will be a buffer. And then the amine end, so the R is standing for a generic portion of an amino acid molecule. NH2, what we can do is, this is the basic thing, so then we can become RNH3 plus, plus H plus, whenever we have a pH that's too low. So buffers for low pH for an acidotic situation. So that's what we have in our bloodstream, and like a buffer in any sort of chemical reaction, you put it in solution and then you can drip, drip, drip your acid in, and it won't change the pH much because of the presence of the buffer, for example. So these are our chemicals in our bloodstream, and therefore also in the interstitial fluid, that are going to help to minimize pH changes. Now, another system that helps with minimizing or helping us out with pH changes that will come into play if our chemical buffering system is overwhelmed is the respiratory system. And we've discussed the respiratory system, how it helps us in, or how it can impact blood pH by whether we hyper or hypoventilate. If we hyperventilate, that means we are blowing off CO2, which means we are becoming less acidotic, so that will cause a rise in pH. When we hypoventilate, that means we're actually keeping too much carbon dioxide in our system, and that will ultimately lead to a drop in pH. So when we say we have a respiratory acidosis, that is caused by hypoventilation. And when we have a respiratory alkalosis, that is caused by hyperventilation. And now finally, we are coming down to the renal control of pH. So our chemical buffers have been overwhelmed, our respiratory buffers have been overwhelmed, and now the kidneys are going to come in and help us to try and control the pH. But this takes time whenever the kidneys actually come into play. Kidneys are helpful because they can rid the body of metabolic acids via this secretion, therefore excretion process. And so we can actually secrete into our filtrate uric acid, phosphoric acid, as well as acidic ketones. And the kidneys are very helpful in doing that secretion excretion process. So down here in our notes, hydrogen ion secretion will come from within the tubule cells itself. The protons got into the tubule cells from the bloodstream and interstitial fluid, and now we will secrete it and move that actually into the filtrate. This will raise, when we secrete protons into the filtrate, that will raise blood pH. And whenever we put protons into the filtrate and therefore urine, we need to buffer this. Let's see here, buffer. And we will buffer this with phosphates, those phosphoric acid, in other words. Phosphates and make phosphoric acid, but also ammonia to ammonium. Let's see here. Let me erase that. Oops. So that can take a proton and make ammonium. So those are the buffering systems inside the kidney tubular lumen. Now, bicarbonate, if we are too acidotic, we would like to retain bicarbonate or create bicarbonate. And if we're too alkalotic, we'd like to get rid of this bicarbonate itself. And so the kidneys are great because they can actually create or save bicarbonate. When you create or save bicarbonate, remember this is done to actually raise our blood pH. In other words, we are acidotic. And it's a really good time now to take a look at this summary diagram. These are all of the buffers that we just talked about. Chemical buffering systems. The main ones that are designed to help maintain our blood pH or minimize pH changes. The bicarbonate buffering system is the most important one, and the bicarbonate buffers the addition of an acid to form a weak acid. So we're referring to a strong acid here. And then the carbonic acid itself can buffer the addition of a strong base to actually form a weak base. We also have protein buffers that we just talked about, amino acids. So if we are alkalotic, we can rob from the acid end, that proton, to help stabilize us. And then also if we are too acidotic, we can put it onto the amine end to also help minimize pH changes. And then also the phosphate buffering system. Then if that system, which doesn't take much time, gets overwhelmed, then coming into play will be the respiratory system trying to help out. And if we increase our respiratory rate, that decreases blood carbon dioxide, which will decrease protons, which will then increase pH, trying to help take care of an acidotic situation. If we decrease our respiratory rate, that increases carbon dioxide, which will increase our protons, which will also decrease our blood pH if we're alkalotic for some reason. And then Also trying to help us minimize blood pH changes are the kidneys, but it takes them a long time to actually come into play. It's not important that we know about type A intercalated cells or type B intercalated cells. We just need to realize that we can excrete protons when we're acidotic, and we can try and bring in bicarbonate to help minimize pH changes, because we want to, if we're acidotic, we want to increase our blood pH. Also, the kidneys can help us to reabsorb any protons that might be in the filtrate itself and secrete bicarbonate if we are having an alkaline pH. And this will help to give us more of a normal blood pH by decreasing that. So that's the end of our chapter on fluid and electrolytes. And when we get back to campus next week, we will go ahead and go into our chapter 28, the beginning of the reproductive system. So we'll have plenty of clicker questions for in-class section over this chapter, as well as the end of our renal or urinary system chapter.